Hi everyone, and welcome to the fourth video on the standard normal distribution. In the previous videos, we talked about how to use the empirical rule, and we found out that the empirical rule does not always apply to all situations that require us to look at regions under the normal curve. And this is where we introduce the concept of the standard um, normal distribution or the standard score. So we will use what we talked about in terms of the standard score into solving this problem. So again, in a certain batch of students who took a 35-point math exam, the scores were normally distributed and the mean was found at 19.9 and the standard deviation is 4.7. The question that we want to answer is if a certain student, Jasper, scored 25.5 in the exam, what percent of the batch scored lower than Jasper? And we already said previously that Jasper's score puts him at this position along the x-axis. We already know that Jasper's score is between 1 and 2 standard deviations away from the mean. But the question now is how many standard deviations exactly away from the mean? And this is where we can make use of the standard score or Jasper's standard score to answer this question. So we compute for the probability that x is less than 25.5. Using the formula for the z-score, this is z is equal to the observed score. In this case, that's 25.5 minus the mean divided by the standard deviation. So using the values that we already know, we should be able to find that the z-score is equal to 1.19. So given that the z-score also represents the actual observed value in the distribution, this notation for probability, instead of writing or looking for the probability that x is less than 25.5, we can also represent this region as the probability or the percentage that z is less than 1.19, given that the corresponding z-score is already 1.19. Now, the next question that we need to ask is what do we do with this value? How do we ultimately answer the question of what is the percentage or what is the area of the region that we see over here? So this is where several techniques would come in. And one of the things that we learned in school, at least for those of us who studied statistics maybe 10 or more years ago, is the use of what we call as the z-table. So what the z-table actually does is it gives us the values of z. It gives us the values of z on the first column together with, but these values that we see on the first column are only up to the 10th decimal place. So since the z-scores that we deal with are rounded off to 2 decimal places or up to the hundredths place, the hundredth digit is actually presented on the first row of the z-table. Now, something that you should need to take note of is that the values that we see in the z-table or the standard normal probabilities that we see here is actually the area to the left. It's always the area to the left of the z-score. So for example, a given value of z, and using the table, the value that we obtain from that table would represent this region over here, which means that if we are interested in finding the area of the region to the right of z, we need to subtract whatever value we get from the table from 1, given that the total area, again, of the region bounded by the normal curve is equal to 100% or 1. All right, so let's take a look at some examples. For example, if the z value is equal to, let us say, negative 2.04, we can identify the area to the left of negative 2.04. Let's estimate that to be somewhere here. By using the table, notice that you have negative 2.0 on the first column, and then the remaining 0.04 should be found in the first row. Now, the intersection of those two values should give us the area of the region to the left of z equals negative 2.04. And that's actually equal to 0.0207. That's 2.07%. So the area to the left of the z-score negative 2.04 is equal to 2.07 All right. Let's make use of that to find the value or the percent of the batch who took the same test who scored lower than Jasper. So knowing that Jasper's score corresponds to a z-score of 1.19, you can now make use of your copies of the z table. I will leave a link in the description box so that you can find a similar copy of the same Z table that I presented a while ago. But if you take a look at 1.19, it's 1.1 on the first column and zero point zero 0.09 on the first row, you should see that this corresponds to a value of 0.08830 or 88.30%. What does that mean? When we interpret it based on the context of the problem that we're working with, that means that 88.30% of the students in the batch who took the test scored lower than Jasper. All right. Now, here are some exercises that you can do to just to help you do understand how the Z table works. So I want you to determine the values of the following based on the Z table. I will present you each item, and then you can pause the video for a while until you find the correct answer, and then you can just play again so that you can see what the correct answer is and compare it with the value that you found. But let's begin with the probability that Z is less than 1.25. Okay, now if you've already found the answer and you found that it's equal to 0.8944, you're actually correct. Let's take a look at the second one. The probability that Z is less than 2.14 is actually equal to 0.983 or 98.38%. How about the third one? Okay, so the probability that Z is less than negative 2.32 is equal to 0.0102. Third, the fourth one, the probability that Z is less than negative 3.13. So that's a very small standard value of the standard deviation. We should expect a very small value here, and that's equal to 0.0009, or that's 0.09%, right? It's 0.09%. Number five, the probability that Z is less than 0.56 is actually equal to 0.7123. Number six, so we're asked for the probability that Z is equal to 0.56. I'll give you time to think about it. But if you are thinking that it's zero, you're actually correct. So you have to remember, one of the properties of the normal distribution is that the probability of exactly a single value is equal to zero. And since the z-scores form or actually part of the standard normal distribution or the standard normal density curve, then the same properties would apply, and this is equal to zero. And if you take a look at number seven, considering both numbers 5 and 6, you would be able to find that the correct answer is equal to 0.7123. So since it doesn't matter, or the probability of Z is equal to 0.56 is equal to zero, combining the probabilities that Z is less than that quantity together with the probability that Z is equal to that quantity is going to be the same probability that Z is less than 0.56. So it's still 0.7123. How about this one? So is it possible for us to find the value of Z or the Z-score for which all of the other Z-scores would be less than or equal to it, and the region that covers that would be 0.1635. So this is where we make use of the inverse normal distribution. We're given the area of the region, but we're after the Z-score. And what you can do if you make use of the Z table is just to scan the whole Z table until you find 0.1635, and then you can identify what Z-score would correspond to that, right? So in this case, you should probably see that it's equal to negative 0.98. But one of the tips that can make use of is if you take a look at all of the Z-scores, the areas in the Z table, notice that the further into the table you go, the lower into the lower portions of the table, and to the right, the larger the values are. So smaller values should be found on the upper portion of the table. All right, let's take a look at some other examples. Now, we're still considering the same situation where a certain batch of students took the same 35-point math exam. But this time, we consider Mika, who scored 18 in the test. Now, the question is, what are the chances that a randomly chosen test taker scored the same or higher than Mika? Right? So let's identify first the location of Mika's score with reference to the mean and the standard deviation using the assumption that or using the fact that the distribution is normal. We can make use of the score 18 to plot it along the x-axis, but what we notice here is that we're working with a standard normal density curve instead. So we need to convert 18 first into the corresponding z-score. So computing for Mika's z-score, we should be able to find that it's equal to negative 0.4. And identifying that position along the x-axis, we can draw the vertical line to separate the total region into two parts, that to the left and that to the right. But based on what is asked, we're actually interested with scores that are higher than Mika. So we're interested in the region to the right of that lines. And that's basically that region. So we're interested in identifying the probability that z is greater than, take note, greater than or equal to negative 0.40. However, if we make use of the z table, remember that what the z table would give us would be the area of the region to the left. And in this case, you should be able to find that it's equal to 0.3446. Now, since what we are after is a region to the right, and knowing that the total region of under the normal curve is 1, we can just subtract 0.3446, the value from the table, from 1, so that we get the probability. This should be the probability that z is greater than or equal. That's very important. It's greater than or equal to negative 0.40. And that's equal to 1 minus the probability that z is less than negative 0.40. And finally, the answer is 0.6554. So interpreting this answer, we can now say that there is a 65.54% chance that a randomly chosen test taker scored greater than or equal to Mika. All right, let's continue with question number 5. So now we're asked what percent of the batch obtained the score between and including 19 and 26. So we need to convert both of these scores into their corresponding z-scores. And when we do that, we should find that z sub 1 and z sub 2, it's corresponding to the score 19 and 26 respectively, should be equal to, negative 0.19 and 1.3. Identifying these the positions of these z-scores along the x-axis, we should find that what we are interested in is the region bounded by those two values, and that's the one that's colored purple on our density curve. That's z sub 1, that's z sub 2. And when we consult or we take a look at the z table, notice that what we will get when we find the value corresponding to z less than 1.30, that's z sub 2, that's going to be the area to the left of z sub 2. In the same way as when we find the corresponding value on the table for z sub 1, which is equal to negative 0.19, that's 0.4247. That's again to the left, the region to the left of z sub 1. But we're not interested in those two regions. We're interested in the region in between z sub 1 and z sub 2. And clearly, when we subtract the area of to the left of z sub 2 with the area to the left of z sub 1, we should be able to find the area between those two points. So that's exactly what we're going to do. To find the probability that x is between 9 and including 19 and 26, subtract 0.9032 by 0.4247, and the final answer is 0.4785. So what we're saying now is around 47.85% of the students in the batch who took the test scored between and including 19 and 26. All right. Here's another one. Suppose the passing score in the test is 12 and the student who either unfortunately failed the test or does very well by scoring 32 or higher will be entered into two separate remedial and advanced programs. What percent of the batch will be entered into these programs? Okay, so using the data that we see over here, we need to convert both of the scores into their corresponding z-scores. But what the question really is asking us to find is the probability that x is either less than 12 or it's greater than or equal to 32. So we're not interested in a certain region in the middle of the normal distribution. We're interested in the region to the left and to the right of z sub 1 and z sub 2. Okay, and these are the two regions here. So z sub 1, the z-score is negative 1.68, and z sub 2, the score is 2.57. And the probability that z is less than 2.57 is equal to 0.9949. All right. So the probability that z is greater than or equal to 2.57 is equal to 1 minus that value. So this is equal to 0.051. That's just the area of the region to the right of z sub 2. So adding the values or adding the areas to the left of z sub 1 and to the right of z sub 2, we should be able to find the probability or the percentage, because in this case, we're interested in the percentage of the students who will either be taking a remedial program or enrolling themselves in an advanced program. And that happens to be 0.0516 or 5.16% of the whole batch. So we now say that around 5.16% of the batch who took the test will either enroll in the remedial or the advanced programs. All right, here's one more. Matt scored higher in the test than 97.98% of the other students in the batch. What is Matt's standard score in the test? So in this way, we notice that the question is actually asking us to reverse the process, similar to what we did in the practice exercises in the previous slide, wherein we're given the percentage, but we're asked for the z-score. So the percentage is 97.98%. Matt scored higher than 97.98% of the students in the batch. What is his corresponding z-score? And since the area to the left of wherever Matt score is covers the percentage of the students who scored lower than he did, whatever score we get from the z table or whatever percentage is given is exactly what we're going to work with. So looking for the value 0.9798 on the z table, we should be able to find that this corresponds to a z-score of 2.05, which happens to be Matt's z-score. All right, so we will end the video here and we will continue with another video where I will show you one of the online applications that we can make use of aside from the z table if you want to solve problems that involve areas under the normal curve.